material and cost as well, but it was an inspired choice, however it happened. If you're going to build a superconducting machine, you have to keep the superconducting material at very low temperatures, so in our case about 4 degrees above absolute zero, and if you're going to do that, you need a very big refrigerator. So we had, for a time, the largest helium refrigerator in the universe, run by this set of people. It's out there across from the ECDF building, now called IARC. So here was the great moment at which the new Tevatron operated and reached the highest energy anybody had attained at that point, 512 billion electron volts. A lot of happiness there, a lot of relief probably as well. More celebrations. So Letterman pouring some substance. Wilson was back for the occasion and was suitably pleased. 4 of my colleagues who were particular heroes of this effort, Alan Tolstrup, Edwards, who designed and implemented the machine with a big team of people, Rich Orr and Dick Lundy, who were in charge of manufacturing the magnets and other things. They're on the occasion here, they're dressed not for work, but because they were at the White House to receive the National Medal of Technology for their fantastic achievements. Okay, so we're accelerator builders at this laboratory. It is the National Accelerator Laboratory. And accelerators can be used not only to go to the highest energies and to do particle physics research, but for medical applications. And for a number of years, the beam for the LINAC was used when it wasn't required for other purposes to make a beam of neutrons that could be used for cancer therapy for soft tissue cancers. So on the right, looking at CAT scans, one of my colleagues who was a leader in this enterprise. On the left, showing off his six-pack abs of steel, one of our radiation technicians, showing how a patient would be arrayed there. So there are a lot of people treated for soft tissue tumors using these techniques. Protons are another way of treating certain cancers, and my colleagues here built a small, compact proton synchrotron for the Loma Linda Hospital in Southern California, which has now treated many people for things like prostate cancer and other things, and which has given rise to a spread of proton therapy for certain kinds of cancer, including a number of centers in this area modeled on the device that they built. Okay, so what's the Tevatron used for in particle physics? There are 2 ways of thinking about it. One is to use the beams of higher energy to use extracted beams and to study what happens. I want to give you 2 examples, both because they took a long time to perfect. It's maybe in the old days, maybe in the high school physics lab, you go into the lab and you get an idea, or you're given an idea, and you do the experiment, and it works or doesn't. Often, what we call experiments are institutions that live for a decade and a half, or 2 decades, in which people come together pursuing some initial goals. They learn better and better how to accomplish those and get new ideas along the way. So this is an experiment to look for the properties of what are called charm particles, those made of the 4th quark and light quarks. And this was the 2nd major experiment in that sequence. The first experiment had a number of near-death experiences, although it had a number of very good ideas in it and produced some intriguing initial results. But there were 2 important innovations here. One was to take advantage of a technology then being developed around the world, but really put into excellent application here, of what are called silicon microvertex detectors. These are detectors that allow you to localize the position of charged particles to a degree that was previously not possible in an electronic detector. And so that was a great advantage. These are particles that decay weakly after a lifetime that's around a picosecond, around a trillionth of a second. And so that means that even at high energies, they travel maybe a millimeter or a little bit more before falling apart. So you got to be able to look very closely. And if you want to gather large samples of them, you have to do it with an electronic detector such as this. So here's a picture of the front end of that detector. The beam comes in. There are little targets there. The targets are interleaved with the silicon microvertex detectors. And this was the first time that such techniques really led to first-rate physics results. Now, there was another challenge here, and that is that if you're taking lots of data and you have to filter out the wheat from the chaff, you have to be able to do computer processing in a way that is fast and cost-effective. Fermilab was always demanding for computing. Here are the first disk drives at Fermilab. So they're about 1 meter in diameter. I think they weighed about 1.5 tons. They spun around very fast, and the total capacity of that is that it would just hold the PDF file of my talk. But we were at the frontier. We did have online computers, PDP-11s for data acquisition. We did have a monster computer, a CDC 6600, which was built of basically military-grade steel. I think it could have sustained a direct hit from a howitzer and still operated. Magnetic tapes. I brought, just for your amusement, since I'm a man of a certain age, this was one of the first computer programs I wrote here at Fermilab. Which led to the discovery of the W boson, by the way. And now, well, okay. So they made all this work, and what enabled the computing was that, again, these are currents that were in the air. It was very expensive to buy computers. Mainframe computers were big and not so fast and so on. So one of my colleagues here, Tom Nash, realized that microprocessors were becoming fast enough, capable enough, you could put enough memory with them. And he and his team started building supercomputers out of little boards and microprocessors. Other people were trying similar approaches around the country and around the world. And over time, this evolved into buying boards, buying computers. We now have the huge farms of computers here at CERN, in the cloud. Amazon and Microsoft and Google are in this business big time. This is one of the places that the idea started, and that people, driven by the need to analyze their data, made it work for the first time. These people also, and you'll see some of them here, together with some of my theory colleagues, built a special purpose machine for a style of theoretical computing called lattice gauge theories. It's a method of solving the theory of the strong interactions. And this has, again, led to great improvements in our ability to understand that theory and to calculate the properties of the proton, neutron, and other particles. So a great achievement. So that was the first experiment I wanted to tell you about. The second is an experiment called KTEV. This is something very subtle. There are particles called kaons, hence the name of the experiment. Kaons plus Tevatron, and they display a slight difference in the behavior of matter and antimatter, which is very puzzling for a long time, and we didn't have all the information we needed about that. So the experiments here, again, this is one of a line of experiments. This is the culmination of a line of experiments. Similar experiments at CERN, a nice rivalry between the two groups, trying complementary techniques. Here's one of their pieces of apparatus, a beautiful crystal calorimeter made of cesium iodide crystals. It's out in experimental areas. Here's their control room, a bunch of them there. Guy dressed in his underwear in the back. So they succeeded over time in comparing the behavior of matter and antimatter and finding a difference of a new kind and giving us a new insight into the way this so-called CP violation, charge parity symmetry violation, happens. And together with their friendly rivals at CERN, were able to give us a new information about that. That all goes into our understanding of leak interaction assessment today. Okay, so another interlude about Fermilab and its natural areas. One of the ideas from early days to make this a really quintessentially American laboratory was to restore the land, the condition it was in before, and that meant restoring a native prairie. So we've had people gathering seeds from the prairie plants, sorting the seeds, planting the seeds, and of course having prairie fires. The point of the prairie fires is that the native grasses have deep roots and the invasive European species have shallow roots. So if you have a prairie fire every year, under controlled conditions of course, you can selectively weed out the invasive species and be left with a native prairie. And so there's a huge area of the inside the ring, as well as some other areas on the west end of the laboratory that have been restored to native prairie. And it is quite wonderful to see when the plants reach this high at the end of the season. We also have, in addition to the Prairie Project, an organization now called the Fermilab Natural Areas. It's an organization of the community and Fermilab people, which takes great pleasure in the natural features of the laboratory, as well as taking care of them. Okay, the second piece of the Tevatron was to go to much higher effective energies, not by hitting protons on a target that's fixed, but by hitting a proton beam together with an anti-proton beam. Now this is a good trick. Protons come out of a bottle of hydrogen. Antiprotons don't come out of a bottle of antihydrogen, so you have to go to great lengths to make them, and to trap them, and to gather them into rather dense beams. This was done in a facility out down to the back called the antiproton source, which there's something called the debuncher and the accumulator, two aspects of it. So we had here at Fermilab the largest concentration of antiprotons anywhere in the world for quite a long time, and used them in two ways. One was to just take the antiprotons and collide them with a target, which might be a gas jet or something, tune the energy to make particles we wanted to. And this wonderful device that I have here is an element of a detector used for that purpose. So this is a piece of lead glass, which has wonderful properties for responding to electromagnetic radiation. Ultraviolet pointer shows you internal reflections so that it gathers all the light back to a place that you can detect it with a photomultiplier tube. It's the same material that's in your grandmother's fancy crystal, used here for detectors, and it's one of the very beautiful objects that my colleagues made. This was a spherical detector in which that's one of the elements. So that's the fixed target purpose. The real goal was, however, to make protons and antiprotons go in opposite directions around the main ring. And to do that, we had to give them directions. So the protons go this way, the antiprotons go this way. As you drove into the main ring road from just behind us, you would encounter this sign, and if you were a jogger or a blader and you wanted to be proton, you could go to the left, and antiproton, you could go to the right. Anyway, that is the way that they circulated. And it was fantastic technology that my accelerator colleagues developed, first to do this at all, and then to do it in such a way that they would make the beams of protons and antiprotons spiral around each other so that they only collided at the detectors where we wanted them to, and not just grease themselves on each other. There are two big collaborations. These were big collaborations in those days, 300, 400, eventually 600 or 700 people, the CDF detector. This is another illustration of the importance of international participation at Fermilab. We would not have started this detector as quickly as we did without the intense participation of Italians and Japanese physicists. They were really essential to getting it started. Others joined us as we went on. And here is the so-called D0 collaboration. Again, this is around the time of the collective discovery of these people, with a bunch of their flags shown here as well. In this very auditorium, in early 1995, there were seminars by the CDF and D0 collaborations in which they announced the discovery of the top quark. This is yet another fundamental constituent of matter. It's something that is much heavier than all the other particles. It weighs as much as an atom of, we used to say gold, but it's really osmium. Anyway, very heavy. But unlike an atom, it's not made up of lots of protons and neutrons. It's just a heat. As far as we know, has no internal structure. So great effort was required to do this. It took 10 years of serious effort at the Tevatron in order to make this happen. It did happen. Here are a couple examples, slightly enhanced. One event from D0. If you know how to look at this, you'll see that the two towers on the left make a W boson. A little stub up on the top is a B quark. This line, the blue line, is a muon. That line is a neutrino that is represented by missing energy. That's another W boson. This stuff down here is another B quark. And that was the signature of a top quark and any top quark being produced. So just a beautiful event in which you can see everything. CDF had their own microvertex detector from early days, and blowing up the vertex there, you can see detached vertices representing two B quarks there, and the other characteristics of this event mark it as a good candidate for a top quark. So that was a big achievement, noticed by the worldwide press. In different languages. Particle physics is over because it's gotten its last secret, something like that. It's never over. So it was a beautiful thing that the two collaborations made the discovery at the same time. They made their announcement of the discovery simultaneously. But there was a little rivalry nevertheless. I wrote an article for our journal Physics Today about the top quark, and I sent the graphics editor of the journal a photograph of CDF and a photograph of D0. CDF, which is on the left, you have to admit, is more interesting graphically, and so that's what they chose. And when this appeared in the mailboxes, my D0 colleagues came to me and said, how am I going to show this to my mother? So we had to have a special run of other ones made with the D0 detector. Okay, another wonderful aspect of Fermilab. This was started in 1980 as our daycare center, children's center. Here are some of the kids from recent times, cute as buttons. And here's a graduation from kindergarten or preschool or something like that. The Children's Center has really been a great thing for our employees and also for some of our summer visitors who come with small children. It's wonderful to have high-quality care available. Okay, let's talk about another thing that we've been trying to find. We believe, on the basis of astronomical evidence and now other astrophysical evidence, it is almost certain that what we're made of makes up only 20% of the matter of the universe, or maybe 5% of the universe all told. The other 20% of the matter, very likely, but not certain, because we haven't found it yet, is made up of a bath of particles in which we're swimming, so particle dark matter. And if it's true that we're sort of sailing on our planet and in our solar system and in our galaxy through a sea of dark matter, then if you make sensitive enough detectors, you want to be able to see a dark matter particle bumping into normal matter now and again. And we've had a number of efforts at Fermilab trying to do this. Here's the cryogenic dark matter search on the left using electronics semiconductor detectors. Here is a modern incarnation of the bubble chamber being used on the right. Both of these enterprises, as well as everybody else in the world, has set increasingly stringent limits on the properties of dark matter, which is not as satisfying as finding it, but is making progress nonetheless. Neutrinos have been part of the Fermilab program from the beginning. When I talked to Wilson years after he left here, he said that everything was going to be good, but he felt that neutrinos were really going to be a big stuff. A special bubble chamber, 15 feet long, was made to do neutrino physics, because you need a big target to detect these weakly interacting particles. It took pictures like the ones that we saw